Hey folks, today we're going to start a three-part series on cache. This first part will cover introduction to CPU memory cache, what it is, the basic idea of how it works, and we'll talk about the direct mapped approach for caching. In part two, we'll talk about average memory access time and the 3Cs, and we'll introduce associative caches. And then part three will focus on how cache affects CPU system performance. So the ideal storage for a computer would be infinite or large, very fast enough to keep up with the processor, and cheap, inexpensive. We don't want to pay more for storage than we do for computing in general. So the size of storage should be able to scale with the capacity of computation. And historically, the computational capacity has scaled exponentially, and so we would like our storage size to scale exponentially. Our speed, we would like it to be approximately able to keep up with 2 storage accesses per cycle so that we can fetch an instruction. And if that instruction uses the data or data memory, then we should be able to load or store while fetching an instruction as well. And it should be cheap. So the first problem is that large and cheap is not fast. So the current and probably into the near future technology for storage of a large amount of bits continues to be the hard disk drive, which relies on spinning magnetic platters. So they physically spin on platters inside of a cylinder. So you can kind of see the cylinder right around there. You can kind of see the little point on the head of the cylinder. That's the head is reading the platter. And there's actually, here we see 3 platters stacked in the cylinder. And we see that you can kind of tell that there's an arm extending over each of those platters. And so there's heads on each of those arms. And so you can read from each platter simultaneously. We call the location underneath the heads the cylinder, generally speaking. But the whole platter is also arranged in a cylindrical shape, so that gets a little confusing. At any rate, you can store a lot of bits nowadays. Modern hard disks are in the terabyte range. They're inexpensive. They cost about 5 cents, 5 pennies per gigabyte, give or take. But they're not fast. It takes about 20 milliseconds to read or write to the hard disk, and that's much slower than the processor runs. Fast is not cheap. It's also not large, as a consequence probably of not being cheap. So static random access memory, or SRAM, is a technology that's basically built on the same idea as a sequential register. If you remember your SR latch or D latch, so the cross-coupled inverter in a bistable loop can store a bit as long as it's got power to it. The SRAM is very fast. It can run at basically the speed of your well within the speed of your processor. The dominant delay to access SRAM is actually the wiring to get to it. So it's about 1 to 5 nanoseconds for an on-chip access, and up to 20 nanoseconds to go off-chip to read from an SRAM, and that's again due to the wire delay. But you can't store a lot in it. You can only store maybe hundreds of megabytes. They don't really make chips bigger than that, in large part because nobody wants to buy them, and because nobody buys them, they don't make them, and so the price is higher because you don't benefit from economy of scale. which means that SRAM chips are not cheap. It costs thousands of dollars per gigabyte of SRAM. So in general, you're seeing SRAM used in multi-megabyte and smaller configurations. So historically, the compromise for system storage is DRAM, dynamic random access memory. The modern incarnation is DDR4. So DRAM is essentially a capacitor which stores the charge that represents value of 0 or 1, and then a transistor to charge or discharge that capacitor. It's not really large, it's kind of medium size. You can get hundreds of gigabytes of DRAM now. That's enough for pretty much most individual workstation workloads. It's affordable, a couple bucks per gigabyte, certainly not as cheap as a hard disk, which was pennies per gigabyte, right? So an order of magnitude more expensive, but not several orders like SRAM. Is it fast? Well, not really. It takes about 100 nanoseconds to read from a modern DDR4 chip, which is off the processor. So 100 nanoseconds read time would be okay to fetch instructions and to access data if we had under a 5 megahertz CPU, which we don't have, since the 5 megahertz CPU would have a cycle time of approximately 1 over 5, so 20. That doesn't sound right. Anyway, you need 2 accesses, so you need about 200 nanoseconds. Oh, that's about right, yeah. So the problem is that since the 1980s or even earlier, and here we see a chart normalizing performance to 1980. So if we took the performance of the processor at 1980 and we took the memory access latency in 1980 and we normalize to that value, then we can see the growth over time of processing throughput and memory access times. And so this is a divergent. They're both exponentially growing, right? We're seeing linear growth, sublinear, but linear growth on a logarithmic scale. So we're seeing exponential growth. But the processor is increasing exponentially faster than the memory speed. And so this is what led to the memory wall, which is the idea that memory is a bottleneck for the computer. The processor can't get enough data and instructions into it fast enough to keep it busy. So the crossing point we can see somewhere here in the early 80s, where the red line shows the CPI, the clock cycles per instruction of processing, and the blue line shows the clock cycles per memory access. And so we can see that the 1-to-1 point, when we could execute the same number of clocks per instruction as we could access DRAM, occurred sometime in the early 80s. After that point, the number of memory clock cycles exceeded the number of core cycles, which means that you could no longer access memory at the same speed that you were executing instructions. Now, this small gap here can be hidden with pipelining. So if you remember, we talked about maybe overlaying the memory access across multiple stages of the pipeline. So when it takes 3 clocks for a DRAM access, you can make your memory access stage into 3 stages. So you divide that up into multiple stages, and that keeps your processor kind of full, okay? And you can do this for both instruction fetches and for data accesses. Unfortunately, as the gap widens, you can't continue to deepen the pipeline enough to hide that gap. And the reason for this is primarily due to the fact that we don't simply execute instructions in sequential order and without dependencies between data loads and subsequent instructions. Whenever there's a control flow control hazard, then you lose everything that you've started to fetch in the pipeline. So if you've got a 10-stage deep instruction memory fetching unit, then you would lose 10 cycles every time you have a control hazard. Since basic blocks tend to be not even that many instructions, then the performance really drops dramatically due to the pipeline flushing or the squashing. And similarly for the data hazards, so remember the load use hazard in a 5-stage pipeline where you have a load unit following an ALU or execute unit. You need a single cycle delay to deal with a load use hazard, right? You need a 1 stall bubble. If the memory unit takes 4 stages, then you would need 4 bubbles for a load use hazard, because you would have to essentially wait that long for the data memory to return the value for a subsequent dependent instruction that needed that value. So this is a big problem, and one way to handle problems where we have a resource that takes a long time to access is to use a hierarchical approach. So here's an analogy of a supply chain, specifically for food. So it takes several months, maybe even, let's say, a year for a full cycle of farming food. And when the farmer harvests their food, then they can distribute it to distributors, and then they can distribute that to grocery stores and markets. And then we can go to a market and buy our food, and it may take us an hour or so. And then we put our food in our refrigerator or even our freezer, and then it just takes a couple of minutes when we actually want to eat something to go and get it. We don't have to wait for the farmer to farm it and harvest it and bring it to us, right? So we've got both a pipeline here, and we have a hierarchy. And the hierarchy here works because we are caching the food that we want close by to us, or the food we anticipate we're going to need in the near future close by to us. So the spatial locality of the idea that we're going to want to access the food that's nearby, and the temporal locality that we want to access food soon in time, or that maybe something we accessed recently we'll want to access again. In programs, spatial and temporal locality come about especially from loop-like structures and from arrays. So both of those kind of basic building blocks of programs exhibit a high degrees of spatial and temporal locality. A loop executes the same instructions repeatedly, and it executes nearby instructions repeatedly. Programs in general execute nearby instructions repeatedly, right? Because when you fetch an instruction, usually you fetch the next instruction. Can't get much more nearby than that. Similarly, arrays are often cycled through iteratively. So arrays have a high degree of spatial locality. You access nearby items in the array. Arrays don't have as much temporal locality, but a lot of data elements do have temporal locality. When you access a variable, you often use it again and again, certainly more than once. So an empirical observation is kind of this 90-10 rule. 90% of a program is spent in 10% of the code. We can extrapolate from that and Amdahl's law that we should optimize that 10%. If the fraction of time is 90, then we want to optimize that fraction 90%. So locality is a property that enables effective use of hierarchical caching. So how does a hierarchical cache work? The basic idea and the terminology that we'll introduce, we'll use another analogy here. So a piece of paper here, we're going to call that a block. So a block or a line is the minimum unit in the cache. So this is what the cache holds. We're going to make our cache units all uniform for now. In general, you don't have to cache identical elements, but it makes certain aspects of caching easier, especially how to find things in the cache and how to replace things in the cache. If you cache elements that are different sizes, then you have allocation and placement problems that become a little trickier. So here's a depiction of my desk. I'd show you my desk, but it's way too messy for this. So on my desk there is one unit of information, right? One page. And I can access it in a second. I can just reach over and grab it, right? So that's a 1 second hit time. Maybe we can think of this as that's my working set of information. So that's my register file right there, right? Access my register file right on the desk. Then I've got this little this document separator. On my desk, my document separator is more of a stack, but you know, that's the way it goes sometimes. Last in, first out. I don't want to know what's on the bottom. So it takes about 4 seconds maybe to access that that document separator, filter through it. So that's my level 1 cache. That's my first level of caching. And then I've got some desk drawers here, and I can open and close those. It takes me a little longer to open a desk drawer than to reach across my desk and grab something in my outbox. So that's my second level of cache. It takes about 8 seconds. So you see it's taking increasingly longer times for me to go and find things the further away they are from where I work. And that's why I keep things close to me that I want to use repeatedly or that I anticipate that I'm going to use again. And then my main memory is my filing cabinet there, and maybe it takes about 30 seconds. I got to walk across the room and look through it and find what I want. So it takes a little longer. It's a slower technology, right? So about 30 seconds. It doesn't stop there. We've actually got to, in a computer, we've got to have some kind of durable storage. Well, for really important documents, we want to have some durable storage for them as well. We don't want to lose them accidentally, and if we run out of room in our little filing cabinet there, we got to have somewhere else to go. And so it's going to take me 100 minutes to move paper back and forth between my main memory and my long-term storage. So it takes a long time to find anything out here, and it takes a long time to get there as well. The warehouse, though, is very effective. It's very cheap. As far as scaling storage and having a lot of paper in one place. So the storage hierarchy gives us an illusion of large and fast storage with affordability. And the way it does that is by using different technology at each level of the hierarchy that best fits that level. So at the top level of our hierarchy, closest to us, closest to the processor, we want to have really fast access, and we don't need to have a lot of data there, right? The processor, a single instruction can only access a limited amount of data, so we only need a limited amount of data there. And so our register file can be small, and we can still make use of it effectively. So our SRAM registers, and then we'll have an on-chip cache, and we'll use SRAM technology for that as well because it's fast, and we don't need our on-chip cache to be all that big either. Maybe we have an off-chip SRAM cache, and then we'll have off-chip DRAM, dynamic random access memory, DDR memory. And then somewhere we'll have disk storage, and that'll be off of the board entirely, but it'll be enormous and cheap, right? So going down the hierarchy, things get larger, and going up it toward the tip, the storage technology gets faster. I'm not going to talk about non-volatile memory here, but it does play a role. It fits somewhere between DRAM memory and off-board disk storage. Non-volatile memories or flash drives. They have higher capacity than DRAM, but they're a little slower typically than DRAM as well. So they sit somewhere in the middle. So caches use SRAM for speed, fast access times within a clock cycle time for 2 gigahertz and below processors, a couple of clock cycles for faster than 2 gigahertz processors. Low density, they use approximately 6 transistors. There's different ways to implement the SRAM, but about 6 transistors to implement it. Takes a lot of power. You've got to keep those transistors going. You got to keep power going through the bistable loop. But it's static as long as the power's on. What you put into the loop stays in the loop. Main memory, we use DRAM for size. Again, it's slower. It's higher density, only 1 transistor plus that capacitor, of course. But it's dynamic. It needs to be refreshed every 8 milliseconds or so. So by now, hopefully, the answer to this question is apparent. Why don't we just use a big L1 cache and not bother with main memory? But you know, the L1 cache is expensive, and so if we wanted to have, let's say 32 gigabytes of L1 cache, well, if we could even fit it on a chip, it would cost us about $32,000. I don't think anyone's willing to spend $32,000 on a single computer. So we divide our storage into the hierarchy in order to best take advantage of both economic factors as well as technological advantages. So density of storage versus the cost of storage. Another thing that we do is to use multiple levels of cache in order to both be able to optimize costs at each cache. So we can have a smaller, faster L1 cache and then a larger, slightly slower L2 cache. And that will allow us to have more data closer to the processor at a less cost on average than if we tried to do something else. And then we can have an on-chip L2 cache, on-chip L1 cache, and then an off-chip L3 last level cache if we need one. So these are 3 typical configurations you may come across. Modern processors are multi-core. They have they're called a chip multiprocessor. They have a multiprocessor on a single integrated circuit or single chip. So a 4-core processor would have 4 processor cores. Typically, they'll each have a private L1 cache. So the closest cache data is private to the core. Often they'll have an L2 cache that is local to the core but can be accessed or is shared. So you may logically think of it as a shared cache, perhaps. You can kind of see what's going on at another core's L2. And then there's a network on the chip, so the on-chip interconnect, and modern processors have the L3 last level cache integrated on the chip as well. There's not usually an off-chip cache used anymore. Memory, the DRAM, DDR4 chip generally, DDR whatever chip, is typically used off chip, still on the board, and then you'll have a storage disk of some sort off the board. So it takes increasing orders of magnitude of access time to go down this hierarchy. So just like the analogy with the paper, to go from the core to the L1 cache takes 4 cycles, to the L2 cache takes about 10 cycles on a modern processor. L3 cache usually takes about 40 processor cycles. So as you have to go farther and farther away from the core to get the data or the instructions that you need, it takes you much longer. Um, and as those times increase, then it becomes harder and harder for the processor to hide that delay. So here's a heat map image of a Intel core from about 2013 or so. And I've partitioned some components of this so that you can see kind of what it looks like on a real chip. So we can see the L2s. This is a 4-core chip, just like the previous diagram. So we see the L2s. We can see a large shared L3 cache. The memory and I/O controllers on the bottom. In the middle, between the shared L3 caches and the L2, that's actually the cores, each individual core themselves, as well as their L1 cache will be somewhere in there. Pretty heavily used. We can see that the L2s and the L3s are not that heavily used, kind of blue, so not that hot. The right-hand side over there, right there, is typically called the uncore part of the chip, because it's not a core. There's some queuing logic there, some other things. On the far side, way over there, I can't even reach it. Okay, on the far side of the chip is actually an integrated graphics unit, generally a GPU or a machine learning accelerator on chip nowadays. So the first problem we're going to look at for caching is how do we actually know where to cache anything. So we want to figure out how do we address elements in the cache, how do we find what we want in the cache, or how do we put something in the cache. And we do that using n bits, and those n bits are the memory address of the data or the instruction that we're dealing with, because that's the only thing we have to really name data or name instructions. So we think of memory as a linear array of up to 2 to the n bytes, logically 2 to the n bytes, for an n bit address. Cache is a linear array, logically a linear array, of 2 to the k bytes, where k is some number, usually quite a bit less than n. And so 2 to the k is much less than 2 to the n. So the cache is much smaller than memory. And we're going to store blocks in the cache. Blocks will be bytes. So some number of bytes, it's usually going to be a power of 2 bytes. So we'll store blocks in the cache as what are called cache lines or cache rows or cache blocks. These are all synonymous, of some size 2 to the m. So the blocks are size 2 to the m. So the question is, how do we find the location for data at a given memory address? I'm going to just ignore instructions. It works the same in an instruction cache as a data cache. They use the same kind of addresses. They can use the same kind of schemes for addressing. So here we look at memory as an array of bytes. So we've got 2 to the n bytes. And I've highlighted here byte number 11. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we want to find out where should we store or look for byte 11 in a cache. So the cache stores blocks as size 2 to the m. So we need to know what the size of the block is in order to figure out where it is in the cache. And the cache is a linear array of 2 to the k bytes. So here we have an 8-element cache. So k is just 3. And what we're going to do is we're going to divide the memory address into 3 pieces. There's going to be a tag, which is going to help us check for sure whether what we found is what we want. There's going to be an index. That's what tells us where exactly in the cache to look for the block. And then there's an offset. The offset just tells us which byte in a block we want. So for actually finding the data in the cache, the offset is not relevant. We need the offset in order to actually return that data to the processor. So the first approach that we're going to look at is the direct mapped approach. And the idea here is to basically rotate through rotate addresses of memory through the cache. So we have 8 blocks in the cache, and so we look at the blocks in memory. We'll map block 0, 1, 2, 3, 4, 5, 6, 7 directly to 0, 1, 2, 3, 4, 5, 6, 7. So there's the direct part. And then block 8 will go to 0, 9 to 1, 10 to 2, 11 to 3, 12 to 4, and so forth. The way to find the address in the cache of a block then is to take the block number and to mod it by the number of blocks in the cache. So block number 11 modulo 8 blocks in the cache tells us that the location in the cache to look for block 11 is line 3. So in this case, the number of bits of the index j is equal to that exponent in the number of blocks of the cache k. So j is k. So when we look at how do we carve up a memory address into those 3 pieces for the direct mapped approach, the offset will have bits 0 through m-1, where there's 2 to the m bytes in a block. The offset uses the least significant m bits. The next j bits are used for the index, and that's going to be the log base 2 of the number of blocks in the cache. Since the number of blocks in the cache is 2 to the j, as we just said, because 2 to the j equals 2 to the k. Log base 2 of 2 to the j is j. So we need j bits to identify the index of the cache, and then the remaining bits from bit m plus j, which is the m and j bits we used in the index and offset, through the most significant bit of the address, n for an n-bit memory address, is called the tag. The tag is used as a comparison to match against whatever is in the cache to see if what we found at the index of the cache is the same address that we're looking for or not. Maybe going through some examples may help illustrate that a little bit more. So we've got those 3 fields. We've got m, j, and n. So we can calculate with those numbers quite a few interesting things about the cache. So we can calculate how large the cache is and how many bits it stores, how many bits not just of the data it stores, but what's its overhead. So what are the tag bits? Every cache block will also have a valid bit in it in the cache in order to differentiate between blocks of the cache that actually hold something we mean it to hold versus blocks of the cache that are just holding garbage bits, essentially. Since remember, the cache is a cross-coupled inverter loop, every bit is always going to have some charge on it. It's going to have whatever charge it had on it the last time it was written. Okay, so we need a valid bit in order to tell us whether or not we should use the values that we read from those rows of the cache. So let's take an example of a 32-bit byte address. So that means that we changed our terminology here. We're going to have a direct mapped cache with 2 to the n blocks, so we'll use n bits for the index. Block size of 2 to the m words, where we'll assume a word is 4 bytes here. So we have 2 to the m plus 2 bytes in the block. So m bits are used to address the word within a block, and the least significant 2 bits are used to address the byte within the word. So sometimes you're going to see there's 2 bits or even 3 bits in a 8-byte word architecture, reserved and called the byte offset. It's a little confusing, but I want you to be aware that you may run into that. So what is the size of the tag field? That's our first question. And we can figure that out by determining the size of the other fields. So the tag field is the total number of bits in the address, which is 32, minus the number of bits we need for the offset and the index. So the offset is n plus 2 and the index is n. So n plus 2. And we subtract that from 32 and that gives us the tag. So the total number of bits that a direct map cache uses, at least to date, is 2 to the n. That's the blocks, right? So 2 to the n is the number of blocks. We multiply that by the cost of each block. So each block has the block size, which is however many bytes we're storing, so 2 to the m words. The size of the tag, we have to store the tag in every block so that we can do a match comparison, and then a valid bit. So if we have a specific setup that asks us to calculate the total number of bits required to implement a direct map cache with 16 kilobytes of data and 4 word blocks, assuming a 32-bit address and a 32-bit word size, we can calculate that. 16 kilobytes is 4K of words, so that's 2 to the 12th, 4,096 words. So now we have 4,096 words, and we know how many blocks we have. With a block size of 4 words, there's 4,096 divided by 4, which is 2 to the 12th, divided by 2 to the 2nd, so that's 2 to the 10th blocks. So there's 2 to the 10th blocks in this cache. From that, we can now determine the tag size, and we can determine the total size of the cache. So each block has 4 words, so 128 bits of data is the block size. The cache is 32 minus 10 minus 2 minus 2. We just distribute that negative sign through the quantity. So that's 18. The total cache size then is the number of blocks 2 to the 10th times the quantity, the block size, 4 times 32, or 128, plus 18 plus 1 bit for the valid bit. So that's 2 to the 10th times 147, or approximately, well, it is exactly 147 kilobits. If we needed to put our answer into kilobytes, we would divide that by 8. If we wanted to put our answer in any other SI prefix, we would know how to multiply or divide by appropriate powers of 10 or 2, depending on what we were working with. So 147 kilobits in order to store 128 kilobits of data, so about 1.15 times as many bits are needed to implement the cache as what the cache is storing. So there's the storage overhead for the cache. So we want to know, how do we know if an item, a data byte that we're trying to access is in the cache, and if it is, how do we find it? We can actually answer question 1 by answering question 2, right? If we find it, then we know it's there. In the direct mapped approach, each block of memory is mapped to exactly one block location in the cache, and so we just look at that block location, and then we need a way to break ties, right? So that's where the tag comes into play. A lot of blocks share locations in the cache based on the modular arithmetic, and we have a very simple illustration of that coming up on the next slide after this one, I think. So let's look at an example of how the cache works with direct mapped cache, assuming a 32-bit word, aligned accesses, and just storing a 32-bit block. So 1 word block and the cache size of 1 kilowords, which is just like the example we just talked about a moment ago. So the 10-bit index is used to select 1 out of 2 to the 10th rows in the cache. Out of that row, we're going to drop down the valid bit, the tag, and we're going to check if the tag of the address we're accessing is equal to the tag in the cache. If they're equal and the valid bit is true, so and it's a 1, so if both the tag in the cache is equal to the tag in the memory address we're accessing and the valid bit is set, then it's a hit. A hit means we found what we want. We'll return the word of data back to the processor. Here we're assuming processors are making word size accesses as well, which is fairly typical. A processor will just discard the remainder if it just wants to access a byte or half word. So that's the basic functionality of a simple direct map cache. This is not yet realistic because nobody stores just one word in a cache row. We'll come back to that. And we're simply exploiting mainly temporal locality here. And we'll talk about that as well. So let's look again at another simple example, an illustration of how direct map caching layers main memory over the cache. So here we have a 4-block cache, and we've got one word blocks again with word size of 32 bits, so 4 bytes. So 2 bits, 2 low order bits, are going to identify the byte in the word, so that's the offset of the word, and we ignore that for the mapping part. The number of blocks in this cache is 4. That's 2 to the second. So there's log base 2 of 2 to the second equals 2 bits for the index. So the middle 2 bits shown in black there are the indices of each of the addresses in the cache. And then the brown bits are the tags. So let's take a look at how this works. So each of these are chunks. I'm going to use the word chunks, technical term, not really. Okay, each of these chunks of 4 blocks sequentially in a row that all have the same tag. You notice 0, 0, 0, 0. The first 4 have tag 0. They map to different locations in the cache, increasing based on the middle 2 bits, right? So the middle 2 bits go 0, 0, 0, 1, 1, 0, 1, 1, and that tells you the row in the cache to look in, 0, 1, 2, or 3. Then when the tag changes from 0 to 0, 0 to 0, 1, then we're in a different set of 4 blocks, right? And they'll map, again, cyclically to rows 0, 1, 2, and 3, and so forth. So each chunk of the memory address space that has the same tag maps to different rows of the cache in a direct mapped approach. And there's only a single row in the cache that you look at to see if the data you want is there. So we check if it's there by comparing the tag that's in the cache with the tag that's being used by the memory address. In this example, the tag can only be one of 4 values, 0, 0, 0, 1, 1, 0, or 1, 1. So 0, 1, 2, or 3. And if one of those is a match and the valid bit is set, then we know that the data in the cache is reflective of the data in memory. It's a cache of what is in memory. So let's take a look at this main memory reference string of words. So assume the word address is 0, 1, 2, 3, 4, 3, 4, 15. So we've omitted the bytes. We've just changed these into block addresses, essentially. So if we have an empty cache initially and all the blocks are not valid, when we access address 0, it's a miss, and we put the tag of address 0, which is just 0, 0, and the value of memory at location 0 into the cache. And we put it in the first row of the cache because the index of address 0 is 0. Now when we access address 1, it's a miss. The tag of address 1 is 0, 0 because address 1 is 0, 0, 0, 1, 0, 0, right? Well, we don't care what the least significant 2 bits are. So the index was 1 because, again, word address 1 is 0, 0, 0, 1 in 4 bits. So the middle two bits 0, 1 is index 1. Address 2 has an index of 2 and a tag of 0, 0. Is again a miss, and we load the tag 0, 0 and the data that's in the memory location 2 into the cache. And then 3 is a miss, so the number 3, the word address 3 is 0, 0, 1, 1, right? So tag 0, 0, index 1, 1, or 3. And so we load the value of memory address 3, or really block address 3, into the cache. So now we access 4. The word address 4 is the address 0, 1, 0, 0. So 0, 1 is the tag, 0, 0 is the index. So the 0, 0 index tells us to look in that 0th row. And we find that in the 0th row, there is an element there, but its tag is 0, 0, which doesn't match the tag 0, 1, right? The tag of memory word address 4 is 0, 1, because 0, 1, 0, 0. So 0, 1 does not equal 0, 0. So we replace the line that's in the cache, row 0, with the value of memory at location 4 with a tag of 0, 1. So that's how a replacement goes. And so now 0, 0, address 0 is no longer in the cache. Address 3 is in the cache. We get a hit there because address 3 is in the cache. We know to look for it at index 1, 1. So the index is 3. And the tag matches. It's 0, 0, and it's valid. So we can get the data there, and it's a hit. 4 is a hit. Now 15, the word address 15 is 1, 1, 1, 1. So that means that its index is 1, 1. So its index is 3. Its tag is 1, 1. So it's going to be a miss because we have a value in index 3, but that value has tag 0, 0, and it's the value of memory address 3. So we're going to replace memory address 3 with the value of memory address 15 having tag 1, 1. So that's a crash course introduction to caching and the direct map cache. This example had 8 requests and 6 misses, so it has a very low hit rate of only 25%, 2 out of 8. In practice, caches do a lot better than that, and we'll see more of that in the future. So the storage hierarchy works because programs have locality. We cache nearby data to take advantage of spatial locality. We'll look at that more closely next time. We cache recently used data to take advantage of temporal locality. And we use parts of the memory address in order to figure out whether and where something is in the cache. So we use part of the cache address, part of the address to index to search the cache. We use the tag to make sure that what we found is what we want. And in the direct map approach, we use modulo arithmetic to map the memory address to a block address. So next time we're going to talk about the 3 C's and average memory access time and introduction to cache performance.